When you are.
Go ahead. Thank you.
Okay, thank you. Yeah, thank you for the introduction. I want to talk a bit about the work we did on evaluating Unikernels as a serverless and function as a service execution isolation environment. Normally, when you think about serverless isolation, you think about one of these three. You, of course, have your containers like runc and Docker, where you get process level isolation, you package your process, all the necessary dependencies in a little namespace, and you go like put that directly on your host, which is very lightweight, but not really secure, which is why there's some secure containers, just like GeoFaaS, which Google uses in their FaaS platform, that add a bit of more isolation in your syscalls, in your file systems, to make everything a bit more isolated and secure. And of course, you all know about micro VMs like Firecracker, which AWS uses for AWS Lambda, which run a full virtual machine, and that's a bit lightweight to make everything more efficient, where you get virtual machine level isolations at the cost of resource efficiency compared to containers. There's a bit of a fourth player now, though, which is Unikernels, which is what we wanted to look at. In the Unikernel, your application is basically packaged along with all the dependencies like drivers, your networking stack, file system, and libraries into a single executable that can run directly on a host or a hypervisor. So there's no more need for a separate operating system like in virtual machines or with containers that use the underlying operating system. Instead, everything that you have is packaged into a single thing that you can basically give to some cloud platform or other platform to directly execute it. And the great thing is that this gives you like lean images, very fast boot times in theory. You get VM levels of isolation. And you also have for security a very small attack surface. It's basically just a hypervisor APIs. There's two kinds of Unikernels out there right now. There's some that are POSIX or Linux compatible, like Nanos and OSV. So these strive to be compatible with your existing Linux environments, which is great. And there's also language-based Unikernels, which are closer to library operating system. You include those in your application, but they're depending on the language that and your application is written in. We wanted to look at the first kind, POSIX compatible Unikernels, because for FaaS, we normally want to have like a known and kind of comfortable execution environment for all different kinds of applications. So for evaluation, we looked at kind of different kinds of execution environments, and we built a lightweight FaaS sandbox experiment harness around those that would allow us to run several micro benchmarks with Go and JavaScript with Node.js to kind of find out cold start times, memory footprints of different isolation environments, resource usage, everything that counts for a serverless platform, especially one that is kind of running in a constrained environment such as edge computing. We compared OSV and Nanos as Unikernels along with GeoFaaS and Firecracker micro VMs, and we used Docker kind of as the standard execution environment. And everything is open source. You can go look at our experiments and find out how to implement those yourself. Our results show that Unikernels are in fact promising. We got great cold start performance with an okay memory footprint, especially compared to Docker. Docker is very hard to beat in terms of everything because it's so lightweight, but of course it's not as secure as the other environments. But we did find that Unikernels right now at least aren't as mature that you can go and use them in production. There are still a few performance bugs in different areas in Nanos and OSV, in I/O performance and CPU performance. And we also found that GeoFaaS had terrible performance, which was kind of surprising. You can find the full results in our paper, of course, and everything like data and tooling that we use to get these results is open source, so you can replicate them yourself. Okay, that's it for me. Any questions, I'm happy to answer in Discord or later in the Q&A session. Thank you.
Thank you very much, Tobias. Great with timing. Valentin, can you share your screen?
Yes. Okay, you should be able to see that now.
I see the screen. Go ahead.
Okay, thank you. Now I'm happy to present our recent work on federated serverless workflows with data prefetching. So the goal of the paper is to optimize total workflow durations of serverless workflows, and these workflows run in a federated setting across cloud platforms. So you could have some functions running in your own data center on some edge locations or in public cloud like Google Cloud Functions or AWS Lambda. To do that, we started off by building a deployer, and this deployer takes in 2 inputs. So first, it takes a set of functions as input, and these are written in a platform-independent manner. And it also takes a deployment specification, and that just determines which function will be deployed on which platform. This deploy adds 2 things to these functions. So first, it adds a wrapper, which we need to turn that platform-independent function into a function that we can actually deploy somewhere. And it also adds our choreography middleware. And this middleware is necessary to handle all of the workflows, and it also does some optimizations. Now, to invoke a workflow, the client just calls the first function of that workflow, and it sends 2 things. It sends the function arguments for that step, and it also sends a workflow specification, and that just determines which functions are to be invoked in which order and on which platform. In addition, if these functions have any extra data dependency, that's also specified in the workflow specifications. And these will also be automatically downloaded by our middleware. Okay, so here we can see sort of a general workflow without data prefetching. And we can see that every function goes through 4 general steps. So first, we have a cold start if there's no instance available. Second, if the function has any data dependencies, we need to download that first. And third, we have a computation part. So here we do some data processing or just basically whatever the user's code does. And lastly, we invoke the next call of our workflow. And we can see here that especially downloading data and the cold starts add a lot of overhead. And the more steps we have in our workflow, the more overhead this adds. So in contrast, if we take a look at a workflow with data prefetching, we can see that we can get rid of this overhead created by downloading data and by the cold starts, since the only phase of these functions that actually depend on each other are the computation parts. So we can start a second function earlier and just move it ahead as far as possible, so only the computation parts need to follow each other. So this way we can basically subtract all of that overhead from the total workflow duration without making the individual functions faster. And the more steps we have in that workflow, the faster we can make it. So we did an evaluation on this, and we used a document processing workflow and tested a couple of different setups on different platforms. So we used AWS Lambda, Google Cloud Functions, and TinyFaaS. And in all of our experiments, we improved the total workflow durations. All of that is open source, and the paper is currently under review, but you can see a preprint on arXiv. Thank you.
You finished ahead of your time, so if there is any question, please feel free to ask it now. And if not, we can move to the next speaker. So please raise your hand if you have a quick question. If not, ask it in Discord, and also between breaks in sessions, we can ask questions. Thank you. Okay, so let's go to the next speaker. Tim, can you share your screen?
Yep, give me just a second.
Okay.
You should be able to see something now.
Yes. Go ahead.
Yes, okay. Yeah, so I'm going to talk a bit about the functions that Valentin just mentioned, how we can improve the result reliability and the efficiency of benchmarking for those FaaS applications. So as Samuel mentioned, there's a bunch of benefits that FaaS in general provides. That's also the reason why there are many FaaS applications currently being developed. Those applications or applications in general receive multiple updates in a month due to the nature of modern development cycles, meaning there are a lot of changes to the function. Here, benchmarking is essential because the deployment pipeline normally contains testing, and testing is very commonly included as it makes sure that the code still functions. Benchmarking, however, is often not included, even though it is very important for FaaS applications, as one of the characteristics of FaaS is the pay-per-use model that we previously already mentioned. The traditional benchmarking approach here is to deploy both function versions separately and then send thousands of requests to each version. However, that approach has several flaws. For example, the underlying instances that run your code could differ, and there are other uncontrollable factors present, which makes the benchmarking procedure in the traditional sense very complicated and very time and cost intensive. That's where we thought that we could apply duet benchmarking in the FaaS environment in general, as it's already been shown that duet benchmarking works very well for micro benchmarks and general benchmark suites. The idea here is that you run both artifacts or both versions on the same underlying instance. You isolate them from another and run them on separate CPU cores and give them access to the shared memory. And then you run them in parallel. That means that all uncontrollable influences that impact your instance will likely influence both versions the same. Here we also did an evaluation. So we compared the duet benchmarking procedure in FaaS to both the traditional and the randomized sequential approach. In the further slides, you will see it as FaaSTrBench. We compared it to both methodologies. We deployed two separate functions, one being a CPU-intensive function and the other one being a RAM-intensive function. We added an artificial performance change to both, and then ran 1,500 experiments both in AA and AB configurations. We looked at two separate things, one being the confidence interval at the max sample size, and we included all experiment results, and also how the interval size develops for all three approaches. So for the traditional, the FaaSTrBench, and also for the duet benchmarking approach. We did this to see how fast each approach can receive an accurate result. All of this is open source and can be replicated. And below you can see a general idea of how the duet FaaS architecture works. So what we found is that duet benchmarking provides way more accurate results with fewer calls made, which makes it ideal for deployment pipelines where you want such procedures to complete quickly. We also found that the configuration options that we added had little to no impact. So CPU or memory intensive both had very similar results. Also, AB and AA configurations were very similar, and duet benchmarking outperformed the other approaches in 99.65% of cases, so in almost all. On the right here, you can see just a quick overview of our memory results. However, the full results you can find in our paper, which is currently still under review, but will hopefully be published soon. So yeah, that's already it. Thank you for listening, and I'm open to any questions.
Yes, so we have time for one quick question if somebody wants to ask. If not, please ask the question in Discord. And also we will have a time in breaks or after talks. Okay, let's, Reza, yeah, I see you already sharing. You have this fantastic setup. Go ahead. I cannot hear you. You are on mute.
Oh, sorry. I'm Mohammad
No
Reza
problem.
Malik Abbasi, Reza for short, and from Scalable Software Systems at TU Berlin. And I'm happy to present our work, GeoFaaS, which is a GeoFF H2 cloud FaaS platform. Just imagine future mobile clients. They are geographically distributed with probably limited battery and computation power, and with many latency sensitive applications. But the widespread adoption of H2 cloud systems didn't occur due to complexities in their development and management. FaaS and function as a service actually for H2 cloud applications is a promising solution. Developers only need to write individual, by now even stateful code functions. But none of existing H2 cloud-wide FaaS platforms are geo-aware. Geo-routing serverless requests will decrease network traffic and ease load balancing, and location measurement itself needs no interaction with the system. We propose GeoFaaS a geographically distributed FaaS platform operating across the heterogeneous edge-to-cloud continuum. It uses the concept of nodes, which are distributed across edge-to-cloud. GeoFaaS nodes manage non-overlapping service areas, defining their responsibility for clients within that geographical region. The cloud node also acts as a backup for edge node failures, whether from resource limitations or internal crashes. GeoFaaS provides the same serverless abstractions through a client library under the hood. The client library simply needs to publish client's requests on a function topic. In the beginning, the client can connect to any GeoFaaS node and send its request. Next, the system will execute the function on closest FaaS resource available and pass the client to the responsible node for further requests. GeoFaaS node actually has 3 key elements. A GeoAware message broker providing distributed pub/sub paradigm, FaaS servers, whether in the same machine or same data center for executing functions, and GeoFaaS bridge, which connects aforementioned elements. GeoFaaS is decentralized, modular, and built on lightweight FaaS systems. It also integrates with existing FaaS services, for example, a public cloud provider, and also acts as a routing layer only, actually. To evaluate GeoFaaS, we implemented a prototype and client library. For a sample function, these topics are used by GeoFaaS. So first, the bridge element subscribes to call topic for each function it is serving and limited to its non-overlapping service area. After receiving a request, it publishes an ACK actually, and then publish the result. The cloud subscribes to 2 additional topics from whole world. First one, number 4, is used by edge nodes to offload the requests transparently. And second one, number 5, is used by clients to directly invoke the cloud. The prototype, including the experiment scenarios, is openly accessible from the link below. And we try to make our experimental environment realistic. We employ 2 edge nodes on individual Raspberries, a cloud node deployed on GCP, and we use hexagonal service areas. And we demonstrate performance and fault tolerance characteristics of GeoFaaS through 3 experimental scenarios. Our experiments demonstrate client's physical distance to FaaS resources, impacts response times, and GeoFaaS effectively executes function requests on geographically closest FaaS server. GeoFaaS transparently offload requests to the cloud under high load, and in case of an edge bridge failure, the requests are transparently routed to the cloud. For full result, please check our paper, which is under review. Thanks.
Very good. That concludes our first session. Thank you for